Okay, welcome, I think, to lecture. Who knows, really? That was very weird. Sorry about that. I logged on. I'm like, wow, I'm like the first one here for like ever, apparently. All right. So we'll give everybody just maybe another minute or so, hopefully, to find all the links and stuff. Well, at least it was good. I didn't really start lecturing to myself. So, at least I figured out, nobody was sitting here with me, I suppose. All right, when we do start, we are going to be we're actually going backwards. We're going to go back into, what is that? I think it's chapter 16. And we're going to talk about complex ions and Kf, which is the formation constant for complex ions and stuff like that. So again, the notes should be up there. Also, the notes for chapter 12, which is the last chapter, will also be up there as well. So pretty much the rest of the semester there is up there and stuff like that. Okay, so looks like I think most have rolled in, so that's good. Again, I'm sorry about that. I'm not quite sure exactly what happened there, but technology is supposed to be good, right? All that good stuff. All right, so like I said, we're going to be going backwards here. So I believe this should be chapter 16. And I believe, like I said, it should be that one section of chapter 16 that we sort of skipped over when we were talking about KSP and all that. So it should still be in that like chapter with the KSP and solubility product. Should be, I believe, the last section out of there. And again, the last section out of there will deal with KF, which is essentially what we've been talking about in the previous chapter when we were talking about complex ions. So this is going to be really the sort of equilibrium that deals with complex ions and all that good stuff as well. So we will get into it, I think, now. So let's talk about that. So obviously, it wouldn't be this class without it being obviously an equilibrium. So one more here, equilibrium, to add to our kind of total of equilibrium expressions and things that we have. This is going to be Kf, and Kf is the equilibrium constant for complex ion formation. And just like everything else that's basically an equilibrium constant value, our expression, we write it the exact same way. So we are going to take our products over our reactants. And just like we would normally do with any type of equilibrium expression, we will also obviously use the coefficients as those exponents, just like we've done before as well. So here goes our products over our reactants. So you can see there with the Cl minus, we did take it to the fourth power for the coefficient as well. So this is the equilibrium constant expression for the formation really of complex ions. And again, that's why it's called Kf. And one thing that we see is as the Kf value increases, the stability of that complex ion will also increase as well. And the idea here is pretty much like a normal equilibrium idea. Obviously, if we have a large value of K, that means that when we do reach equilibrium, we should mainly have products. And as you can see in this case and how most of these guys are written, our complex ion is over here on our product side. So the larger the Kf value, the more products you should have. The more products you should have, that means that you obviously would have more complex ion being formed, and you would obviously then have obviously a more stable complex ion sort of being formed. And now that we've did the last chapter there, we pretty much can figure out exactly how to name all these guys. So you should be able to name that guy right there, something like tetrachloral cobalt 2 ion, right? Just like hexaquo cobalt 2 ion for the guy on the left there, on the bottom left of the screen or the slide. And as we've talked about, we will see sort of different colors depending on the sort of the ligands that are attached and also sort of the charge of the complex ion metal that's involved. So here they're both oxidation state of +2 for our cobalt, but you can see one with the chloride as our ligands attached does give us sort of that blue color. One there with the water attached as our ligands gives us more of that pink color. So this is the KF value. And what we will see sort of in this chapter, and what we'll see a little bit later at the end in terms of a table of KF values, or as we sort of are working through some of these problems, in general, the KF values are very large. So just in general, these formation constants are very, very large numbers. So it's very similar to how the KSP, for the most part, was super small numbers, right? Which meant that they mostly were insoluble and we had reactants. Our KF values are typically super large there, which means that typically speaking, we will want the complex ion being formed. So this will also explain some of the things that you've seen perhaps in like group 1 qualitative analysis. If you remember, part of the steps of group 1 qualitative analysis was that you basically had silver chloride, and to verify that you sort of have the silver, you added ammonia to it. And when silver and ammonia come together, they make a complex ion. And it's that formation of complex ion which is really, really favored. And that's how we could able to basically get rid of the solid silver chloride or free the silver from the chloride, because the KF value is so large. Complex ion formation is a lot of times really, really favored. So as we talked about sort of in the last chapter about ligands and sort of the idea of coordination number, the idea here is that the ligands are these Lewis bases, which means, again, they will basically be donating a pair of electrons. And when they donate a pair of electrons, they're basically donating them there to the metal, which is basically electron deficient, hence the positive charge. And it's more like an acid-base sort of situation that occurs. But importantly, as we talked about, all these ones that we see on the screen here are the type of ligands that are referred to as being monodentate, which, as we discussed in the previous chapter, means that they will bind in one place per molecule. We also talked about some ligands having the ability to bind in multiple places per molecule. So like our EN or ethylenediamine, our oxalate, those are two very sort of popular examples of bidentate ligands, which again, you get sort of, as we talked about, like a 2-for-1 situation occurring. For every one molecule, for example, of oxalate, both of the oxygens there that are single bonded are able to bind into the metal, and you get sort of a 2-for-1 situation. We also saw the EDTA, which is that one that can bind in like 6 different places per molecule, which really can tie up that metal really, really well. That also led us to last chapter, and also a little bit in this chapter as well, right? The idea of coordination number. And because some ligands can bind in more than one place, that means, again, that it doesn't necessarily mean that the little subscript that you see there will be the coordination number, right? So especially for something like that EN or that oxalate, again, you have to take into account how many times they can bind per molecule. Again, because coordination numbers definition is just that, it is the number of donor atoms that basically they're there. So it's how many atoms are directly attached to it. So in this case, in these two examples, again, both of those ligands are monodentate. So there are 6 waters. Each of the waters are going to attach in via the oxygen, and that gives us a coordination number of 6, while the Cl- is there. And the second guy, again, going to be monodentate, since there is only obviously one atom there in terms of Cl minus, and would give us a coordination number of 4. The other important thing, right, to remember is, as I think we mentioned as well, but just to reiterate, essentially these ligands do attach to the metal one at a time. So that's sort of important about what we're going to talk about in this chapter and in terms of KF and sort of the equilibrium of it. So for example, if we take this guy right here, basically what we got going is we have 4 Cl minuses that are going to be attached. And these do happen, as I mentioned, basically one at a time. So the first thing that would happen is we would slap on a Cl minus, and we would get something like COCl plus. And you could have a K value for that sort of process. The next thing would happen is that COCl plus would add on another ligand, giving us, you know, our sort of normal ionic compound in that sense. Also can have an equilibrium constant associated with it. Then our next guy will put on the next Cl minus. Also could have an equilibrium. And then the last step here, I'll just go over here, will be this guy putting on that final ligand. And this guy also would have a K value associated with it. So these do happen sort of in a stepwise fashion, almost like how acids sort of lose H pluses, right? They lose it basically one at a time. And sort of similar sort of process here in sort of putting on our ligands. Now, what we usually think about it, though, is the overall reaction. And I guess it would have been better if I kind of drew them together. But if I added up all 4 of these steps, essentially, again, we could cancel out things that are the same on opposite sides of the arrow. So this guy and this guy, right and left of the arrow, right and left of the arrow, right and left of the arrow will basically cancel out. And if you add all 4 of those reactions together, you're left with sort of the overall reaction that we sort of think about, which is the cobalt then adds here 1, 2, 3, and 4 Cl minuses. And the only thing left that you can see on the right-hand side is our complex ion, which is all said and done. So sometimes we think about sort of the overall reaction that's happening, and especially in these sort of KF problems, sometimes you do have to sort of think about it in a stepwise fashion to get there. And a reminder, right, as we learned way back when, if this was, say, K1, K2, and K3, and K4, if I wanted the KF for the overall reaction, hopefully we remember that what we do with our K values is we would actually multiply them, yeah? So we take K2 times K1 times K3 times K4. So remember that when you're adding reactions together and you're dealing with equilibrium constants, we don't add them, but we do multiply them. I hope you did that yesterday on the exam. But again, a reminder is something we learned from the beginning of the class here. So there are certain situations in some of these problems that we're talking about where it's sometimes more advantage to sort of look at each of the steps individually, just sort of based on the information that's given to you. Sometimes there's a little bit more of an advantage to sort of add up all the steps together and just look at sort of the overall process of all the ligands being added. And to be truthfully honest with you, as we will see in an example here coming up, that it really doesn't matter in the sense because these are all equilibrium sort of expressions, reactions, which means if you do have some equilibrium concentrations, you could pretty much put it into any of these sort of equations and you actually get the same answer. So keep that in mind. It may not make 100% sense yet, but when we get to sort of that examples that sort of deal with it, hopefully it will. So let's take a look at an example here together and sort of figure out, how we should approach a problem like this. So we're going to take 0.2 moles of copper 2 sulfate. We're going to mix it with a liter of 1.2 molar ammonia. What is the concentration of the copper 2 ions at equilibrium? For this particular problem, we're going to assume that the total volume remains 1 liter. So that's just an assumption. Won't always obviously be the assumption that will happen here, but we're going to sort of make that assumption as it is sort of a good idea here. So let's talk about how we should approach these problems. As you could probably imagine, it is an equilibrium constant, and that means our favorite thing should come back, right, which is ice tables. So an ice table approach here is probably what you should be doing. So let's take a look at that. Let me rewrite the equation here. So we have Cu2 plus 4NH3, and it goes there to our CuNH3 2 plus, and our K value. Let's take a look at a couple of things here. So we are going to need sort of our initial concentrations here for our ice table. So we need to figure out their initial of copper and our initial of ammonia. So we're going to again make that assumption that in this particular problem that the total volume remains 1 liter, which means if I take 0.2 moles divided by 1 liter, my initial concentration of my copper is 0.2, and my initial concentration of my NH3 would be 1.2, again, assuming everybody remains 1 liter. Now, the other important thing when we look at it is the K value. So that's 5 times 10 to the 13 is the K value. So KF equals 5 times 10 to the 13. So we're going to put into our table, initially, we have 0.2 molar of our copper. We have 1.2 molar there of our NH3. And like normal, we're going to zero out our product side. Now, normally when we do an ice table like this, and I'm going to write it, I think, in red, just to highlight it real quick. Normally when we get to the change part, we would do our x's. So this would be minus x, right? This would be minus 4x, and this would be plus x. Okay. So something a little bit different when we sort of take the complex ion approach here is based off of the K value here, we have 5 times 10 to the 13. So I won't venture to tell you how big that number is, but that is a very big number, I'm assuming, at 10 to the 13. And what that means is, if you think about what we consider a large value of K, which is 1, right? Anything above 1. And 5 times 10 to the 13 is definitely way above 1. That means that pretty much this entire reaction, even though it is a reversible reaction, is pretty much 100% heading in that direction towards our product side, right? It is 100% heading to the product side. So what that means in this particular case is what we know is going to happen is we're going to assume that in order to make our product, right, the center part of what is our product is the metal. The metal is basically sitting in the middle of the complex ion. So because that K value is so large, we're going to assume that almost 100% of everything is going to our product side. So what that means is we can make the assumption when you do KF type problems that the change is actually going to be the metal part. So the metal will be our change part of it. So instead of using X's, we typically will use the metal and actually use numbers here. So very often what people will do is they will kind of combine the initial and the change together in this change step, and we would say we would have 0.2 minus 0.2. We would have 1.2 minus 4 times 0.2. That's equivalent to like 4x, right? And this obviously is equivalent to x. So again, this is sort of what we're doing here, right? And on this side, it would end up being 0.2. Any questions on that part of the table so far? So very similar to sort of what we do when we do like maybe titrations or buffers where we sort of know what the change should be. Here we do kind of use it. We kind of combo the initial and change together. That way when we get to our equilibrium, we end up with 0 for our copper 2. We end up with 0.4 molar here. And we end up with 0.2 molar here. First off, any questions on, again, that table? It's basically the same idea as using X, except we kind of know what X is in this case. We make that assumption that because the K value is so large, all of the metal should definitely be used up and be part of that complex ion, which means we shouldn't have any metal left over. Any questions on that so far? So the question and the problem was, what is the concentration of the copper 2 ion? So clearly it can't be 0, otherwise there's not much of a problem to do. But the reality of the situation is, and some of the stuff that we've sort of learned over the semester is, even though people say it's like 100% something, always going to happen that way, like in solubility, right? We always think about, as we talked about, silver chloride is, you know, always being insoluble, right? But there are situations where it could obviously be soluble and there's some degree of solubility. And that's because of the nature of a reversible reaction is it's reversible, which means even though almost 100% of it has all gone to the product side, there's still going to be a very small amount of it that's going to head back the other way towards the reactant side. So although we zero out the metal in these type of problems, what we then do is try to figure out what that value is. And we could do that by, even though we zeroed it out, we can now come back and go, we're going to call my value of the free copper 2 in this case, X. And we're going to try to solve for X. And how we're going to do that is we're going to use our equilibrium expression here to help us. So Kf would be the concentration of our products divided by our reactants. And again, we want to remember that we do have to take that to the fourth. And that's going to equal 5 times 10 to the 13. So basically, we could substitute in our equilibrium values for everybody. So that will give us 0.2 divided by the concentration of copper 2 times our NH3, which is 0.4 to the fourth, equals 5.0 times 10 to the 13th. So by using our equilibrium expression, by even agreeing that 100% of the copper 2 should be tied up, again, there's going to be a little bit of it coming back, which means when we do solve for the copper 2 concentration, we should expect the value to be very small for the free copper 2 that's still in that solution. So if we do a little solving of this, basically these two guys switch places, and you end up with 0.2 divided by 5 times 10 to the 13 divided by 0.4 to the fourth will equal our copper 2. They basically just swap places. And if you do all that good math, I got a calculator here somewhere, I guess. Let's see here, 0.2 divided by 5 to the 13 divided by 0.4 to the fourth. We get 1.6 to the minus 13 as our free copper 2 concentration, 1.6 times 10 to the minus 13 molar. First off, any questions on that calculation? Now, remember that the assumption that we make in these problems, there's really two assumptions that you make in these problems. And the two assumptions that you make in these problems are, A, all of the free metal should end up in the complex ion and get used up completely. So we assume that the change part in these reactions is always the metal ion, not the solid metal. There's no solid metal. So the metal ion that's basically floating around in the solution. And B, the second part of that assumption is when we actually do solve for the free metal ions concentration, it should be a really small number. And as we can see here, 10 to the minus 13 is a small number. So both of those sort of values agree with the assumption that we made that we should have pretty much no free copper 2 ions floating around at a concentration of basically point and then 12 zeros, 1, 6. You pretty much don't have any copper 2 pretty much floating around. But technically speaking, with quotes, there is a certain super small amount of the free ions still floating around. Any questions on that there? Yeah, so the KF value would be given to you. So it's a value you could find in a table like a Ka value, a Kb value. So we'll see a table at the end here of some KF values, but either they'll be given to you or they are in like a table that you can look up and stuff like that. Yeah. Other questions on that? All right, so why don't you try one and see how you do, how far you get there. So this one's a little bit different, but see what you come up with. We want to calculate. So x is equal to 0.2 because that's one of the assumptions that you make when you do this type of problem. So when you do this type of problem, which is a KF problem, typically speaking, as we'll see a little bit later, all the KF values that you see are super big numbers, really large numbers. And what that essentially means is because they're larger than sort of large numbers, you know, again, when we think about a large number for K, it's like 1 above 1. So 5 times 10 to the 13 is way above 1. So essentially what that means is because those KF values are extremely large, that means that pretty much, even though it's a reversible reaction, this reaction is pretty much heading all of it in like a one-way street towards the product side. But in reality, it's still a reversible reaction, but that's sort of the assumption we make that is so large, 100% of it has to go to the product side. And because on the product side, it's always the complex ion. And remember that in order to have a complex ion, you need the metal in the middle, which means in order to make all those products, you got to use up all of the metal that's there. It's kind of like the limiting reagent in that case because of such a large value of K. And that's why when you do these type of problems, the change part is always the metal that's part of the complex ion. That always gets used up first because it's kind of like the limiting reagent, right? As soon as you get rid of that metal, there's no possible way to make the complex ion. So it's 100% going to get used up. And the 0.2 was the amount of the free copper 2 that we started with in that case. Other questions on that? Okay. So why don't you guys give this a few minutes or so, give it a try, and we'll see how we do and what you come up with. So we're mixing these two solutions together. And here we don't have the overall, but we do have the stepwise sort of formation that's happening with the K values for each of those. So again, see what you can come up with here. We're looking pretty much for everybody's concentration at equilibrium. So see what you come up with. In about 3, 4, 5 minutes here, we'll talk about it and see how you're doing on it. Okay, so let's take a look and see how we're doing here. All right. So in this case, we're pretty much looking for kind of like everybody's concentration. We are given basically that we're going to be mixing 150 milliliters of 1 times 10 to the minus 3 molar silver nitrate with 200 milliliters of 5 molar sodium thiosulfate. And we're going to mix these together basically to make this complex ion form. And what we're given here, again, as I mentioned at the beginning, not the overall sort of formation of it or reaction of it, but sort of the stepwise formation that happens. And again, as you can see, again, that ligand, which is the S2O32 minus, gets added basically one at a time here. And until we get both of those. So we do have equilibrium constants for each of the steps that occurred. So really the first thing that we sort of want to figure out is really our metal, which is the silver ion, and our ligand, which is the S2O32 minus. We really want to kind of know what the concentration of those guys would be when we sort of mix them together. So basically that is what we want to maybe start out with first. So if we wanted to figure out the concentration of the silver that is present, this silver nitrate is the only source of our silver that's present. So really we could do an M1V1 equals M2V2 type calculation. And if we do, we have 150 milliliters of the silver nitrate. And if we times it by the concentration of the silver nitrate, and divided by the total volume, which would be 150 milliliters plus 200 milliliters, gets us to 350 milliliters. Again, when you use the dilution equation, you don't have to worry about converting. You can convert it to liters if you want. You could leave it in milliliters as well. And again, you'll get the same answer. And if we do that, we get 150 times 1 to the minus 3. Divided by 350. We got 4.29 to the minus 4, it looks like. So 4.29 times 10 to the minus 4 molar would be the concentration of our silver ions in this mixture, again, supplied by the silver nitrate. We want to also figure out what is our ligand's concentration there, which would be this guy. Going to do pretty much the same calculation here, except that we have 200 milliliters times the molarity of that, which is 5 molar, right in underneath, also divided by our total volume, which is 350. Again, the milliliter is going to cancel, going to give us 2.86 molar in that particular case. Any questions on that so far? All right, so now we can kind of maybe start working on the problem here. What I'm going to do is I'm actually going to take both of these reactions here and I'm going to add them together to get our overall reaction. And if we do that, just gonna move some stuff out of my way here. There we go. So basically I'm just gonna put a big plus sign there. Draw a really bad straight line. There we go. And what I'm going to do is add these together. So again, opposite sides will cancel. So that will cancel. That will leave us the overall reaction, which is the silver plus a couple of these ligands coming together, giving us our complex ion here, which are silver. Now, if we want the Kf for this, we could get it by multiplying both of these together. So if we multiply both of those guys together, 7.4 to the 8 times the 3.9 to the 4, we actually get a Kf value of like 2.89. We'll call it, we'll round this to 2.9. 2.9 times 10 to the 13. So here we see as well, we ended up with a fairly big Kf value, which is what we normally will see in these sort of problems. So what we're going to do then is continue on. So I'm going to rewrite the overall reaction. So at this point, I'm going to work with kind of the overall reaction that's taking place. And if I do that there, we got our overall reaction, which was our silver plus our 2 ligands going to our complex ion. And at this point, we can do our ice table. So initially, we calculated that the initial concentration of the silver when I mixed it was 4.29 times 10 to the minus 4. It was also 2.86 molar, right, for our ligand. This would be 0. Again, here we saw that the Kf value was pretty large, and it is complex ion being formed here. So again, it's usually pretty safe to make the assumption that in this particular case, even though I double arrowed it here, essentially because of that K value, you know, it really is all almost 100% heading towards the product side. And what that means is, just like what we saw with the copper in the previous example, we should expect that all of the silver gets pretty much used up. And when we do solve for the silver, any free silver that's still there should be a really, really small number. So we're going to do kind of the same thing. The change here is going to be basically 4.29 times 10 to the minus 4 minus 4.29 times 10 to the minus 4. This will be 2.86 minus 2 times 4.2 times 10 to the minus 4 as I crawl over to this side, and this will be plus 4.29 times 10 to the minus 4. A reminder that the 2 here is the same idea as the 2x that we normally do in an ice table. That means when I reach equilibrium here, as we expect, most all of the silver should be used up. We will end up with basically still 2.86 for our ligand and 4.29 times 10 to the minus 4. Any questions on that ice table there? Now, from this first ice table, we actually solved for a couple of pieces of information that we have. We have solved for, let's see here, the concentration of our ligand, which I think was one of the things they were asking for, maybe not, is a concentration of 2.86 molar, again from here. We also figured out the concentration of our complex ion, which I know they asked for. Has a concentration of 4.29 times 10 to the minus 4 molar. And now we actually do have a couple of options as to how you can sort of proceed at this point. And I'm going to sort of explain to you a couple different ways to sort of do it or sort of approach it at this point. Let's go back to the actual question. So after doing our first ice table, we were able basically to figure out the concentration of this guy at equilibrium. Now, because we have these stepwise equations here, one approach that you could do is look at the second one, for example. And if you look at the end of your ice table we just did, again, we have this concentration, and we also have this concentration as well, which means we can use just the second equation by itself and figure out the concentration of our AgS2O3 minus by using sort of that equation as a standalone sort of problem. So let me do it that way first, just to kind of show you. So again, going from equation number 2 here, using our K2 value, we get that the K2 was, again, 3.9 times 10 to the 4. And just like if we were to write an equilibrium expression for just the second equation there, it would be our products over our reactants. So it would be our complex ion divided by these two guys. So let me write that there. So it's going to be our complex ion divided by the one guy we're looking for, which is the silver with the one ligand attached. Times the ligand. And again, we could use the second one because from this table, there's the concentration of our ligand, and there's the concentration of our complex ion. So we actually could put those values in. And if we do that, 3.9 times 10 to the 4 equals 4.29 times 10 to the minus 4 divided by the concentration of sort of our intermediate we're looking for. And then the ligand had a concentration of 2.86. So solving for the guy here, essentially mathematically speaking, these two guys are going to swap places. And if you do that and solve it, you'll get that the concentration of the AgS2O32 minus there is going to equal a value of, I believe, 3.8 to the minus 9. Double check real quick. And you will end up with 3.8 times 10 to the minus 9. If you have your calculator in scientific notation, if you don't, then you have a whole bunch of zeros with a 4 at the end of it at that point. Any questions on that so far? And again, the purpose of this was because one of the things asked in the problem was, what is the concentration of what we just solved for? Now, following sort of this path of kind of using the stepwise sort of equilibriums, once we just solve for what we just got in that answer, if you go back now to the first equation, you now have the concentration of this guy, which we just solved for, and you still have the concentration of this guy here, which means you can now go back to the very first equilibrium expression and use that to figure out the amount of silver that's present. So let's do that, kind of finish it up in this approach, and then I'll kind of show you what you could do as well. So let's take a look at this guy here. So if we look at K1, and again, from the problem, that's where we got the K1 value, and it is 7.4 to the 8. And if we write the expression for the first one, it is our products, which is this guy. Again, in the first stepwise equation is what we're looking at here, divided by our silver concentration and this guy's concentration. And again, we have all these values from our previous two things that we solved for. So we just got that this is 3.8 times 10 to the minus 9. The silver we're looking for. And we saw that this guy is still 2.86. Again, mathematically, these two guys are going to switch places, and that's going to give you your silver is equal to, and again, if our assumption is correct, we should see that the silver should be a relatively small value. And if you do that, you get a silver value of 1.8 times 10 to the minus 18 molar. And I would definitely agree that that is a very small amount of free silver ions that are floating around. essentially what we got is all of it in the complex ion. But again, because it's a reversible reaction, there is still going to be that very super small portion that will be free. And to the minus 18 essentially is none there. But technically speaking, there is some there. So what we just did there demonstrates that because in a stepwise fashion and you get those equilibrium constants, they're all equilibriums, right? So as once you figure out the equilibrium constant of somebody that's in those equations, you can use them individually to figure out what you're looking for. Now, I did say that there's sort of a different approach that you can take, and I'm just going to show you the different approach that you could take here with the silver part of it to kind of go that path first. So if we go back to our original equation that we wrote here, and again, this was our overall reaction, right? And we did calculate that KF for that, which was 2.9 to the 13. So really this guy is 2.9 times 10 to the 13 is the KF value for this guy. We could have, just like we did in the very first problem, once we got to here, come back and go, we're going to call this X, just like we did in the very first problem, right? And you could have, if you wanted to, actually solve for silver plus, the Ag plus concentration first. So to show you sort of how that looks, if we went from the overall reaction using our KF value, so again, the KF that we calculated for the overall reaction, 2.9 to the 13. If we take the overall reaction and write the equilibrium constant, the 2.9 times 10 to the 13 came from here. So when we add both of the steps together, you multiply these K values together to get the overall K. So when you add reactions together, you actually have to multiply the K values, and that's how you got to that value. Okay, so we're going to take our overall reaction and write our expression, which would be our complex ion, divided by the silver concentration times the S2O32 minus, and because it's the overall reaction, we do need to square it from the coefficient that's there. And again, just like we did in the first problem, we can basically call silver X. So we would end up with 2.9 times 10 to the 13 equals our 4.29 times 10 to the minus 4. And again, I'm getting that number from our original overall reaction table here. And I'm going to use the 2.86 for the other guy. So we're going to solve for the silver. And our 2.86 squared. And if I didn't screw up, again, these two guys should pretty much swap places. We should end up with the exact same answer as we have above. Otherwise, I'm going to be embarrassed and shut the video and all that and walk away slowly. So let's see. Oh, good. I don't know if that's good or bad. I get to stay. That this is silver concentration 1.8 times 10 to the minus 18. So you can see it is obviously the exact same as we got there. So this problem does demonstrate a couple of things. If you want, you can use sort of the stepwise fashion. Yeah, so I think if I understand your question, the 4.29 value here was the original value of the silver, and that came from the silver nitrate. So remember, it was kind of like that moment right when you dump it in, right? It's coming from that silver nitrate. It's going to break apart into free silver ions, and then obviously it's going to start picking up, as you can see, probably pretty quickly here with the ligand and form that complex ion. So what is left of that 4.29 times 10 to the minus 4 value of free silver ions is we're down to 1.8 to the minus 18. So pretty much all of it's gone. And that's sort of the major assumption that we do with these complex ions is because of those values are so large for those Kf values, pretty much they want to form those complex ions. And when they get near each other, when a good ligand and like a metal like silver or a metal like copper or something like that get near each other, they're going to pretty much ignore everybody else because they're going to want to come together because of that really large value of the Kf. So again, this demonstrates that you can, if you need to, use the stepwise sort of fashion. In this particular problem, because we were asked really for this guy's concentration, at some point we had to use sort of the stepwise approach there to get to it. Or you can use that overall reaction like we did before. You can see it comes out the same way. Any questions on those two there? All right, so let's take a look then at another sort of wrinkle on this. And let's take a look at this problem here and sort of see what we come up with. In this particular problem, we want to calculate the molar solubility of silver chloride in 1 molar ammonia, NH3. And this right here is essentially what's happening. These two reactions are essentially what's happening in group 1 when you do your qualitative analysis. If you remember, in group 1, you have that silver chloride that's a solid. You add some ammonia to it, and before you know it, you have that complex ion. All of the silver is basically, went away and stuff like that. So what we're looking for is actually the molar solubility of the silver chloride in ammonia. So really, to get what's truly happening here, we need to add both of these reactions together. So if we add both of these reactions together, I'll just do it right here since it's all together. The silver ion itself is actually going to cancel out as it's on opposite sides. And that's going to leave us really the overall reaction that it is talking about in the problem. What happens when you take silver chloride, which is a solid, and you add some ammonia to it? You are going to form this complex ion. And some chloride, right? And to get the K value for this particular reaction that we're actually looking at, doesn't matter if it's a KSP and a KF. And hopefully you're saying to yourself right now, there's like 8 minutes to go in lecture. That's what you're probably saying to yourself. But hopefully besides that, you're saying to yourself, it doesn't matter because a KSP, a KF, they're all really equilibrium constants. So you can multiply those guys together to get the K value for this reaction. And it's very similar to the idea of like when we take Ka times Kb equals Kw. It doesn't have to really be the same little letter on the bottom. Ultimately, they're all the same thing, even though they have the different descriptions. They're all really equilibrium constants. So even though, again, it may seem weird to you that that's a KSP, that's a KF, you could actually multiply those guys together. And if you do that, you will get the equilibrium constant for the combined reaction, which looks like it is perhaps 2.4 times 10 to the minus 3. Any questions on that so far here? All right, so because we're really looking at this overall reaction, that is really the reaction we're going to work with. So let me get some fresh page and rewrite it. So what I'm going to rewrite here is really just the overall reaction that we are looking at. And the other thing that's a little bit different than the ones we've done before here is we're not really looking necessarily for the metals concentration, the free metal, we're actually looking for the molar solubility. So when we think about molar solubility, that should probably, hopefully in your head, make you think about KSP and sort of how we do KSP type problems. And how we do KSP type problems is how we're going to approach this problem here. And we're going to do an ice table. And really the only number that was given to us is we are dumping in there 1 molar NH3. And that means we could go 0 here and 0 here. Now the change part here, since we're sort of doing like a KSP table looking for the molar solubility, right, which is what S stands for, we could do our molar solubility by doing minus 2S plus S and plus S. Again, the 2 is from here, just like normal. A little bit different is in most of those solubility ones we did, we had nothing on the left-hand side, but here we do because we are dumping in there the ammonia. And that means when we get to our equilibrium, we will have 1 minus 2S, S, and S. Now, the question is really asking about this guy. So he is a solid, so that is why I haven't really put anything here. But we'll talk about sort of how we get back to him at the end. But that is ultimately still what we're looking for in terms of our answer. Just like normal, we're going to put this into our equilibrium expression. And for this guy, the K would be the concentration of our products divided by our reactants. And we do need to square it, right? So putting those values in, that's going to give us S times S divided by 1.0 minus 2S squared equals the K value that we got previously, which was 2.4 times 10 to the minus 3 from multiplying both K values together. Just like normal here, we're going to solve for S, and S is going to be our molar solubility. So hopefully you could also recognize that this is a perfect square. So I'm just going to put a giant square root on both sides. And when I do the giant square root on both sides, that will give me S on top, 1.0 minus 2S on the bottom. And I'm not going to hopefully forget to take the square root of that other side. So when we do that now, square root of 2.4 to the minus 3, going to give us 4.89. I guess I could have rounded 9 times 10 to the minus 2. We're going to multiply the bottom to the other side. That's going to give us S is equal to, I'll round here, 4.9 times 10 to the minus 2 minus 2 times that, 9.8 times 10 to the minus 2S. We're going to bring that S to the other side and basically add 1 to it. And then we're going to divide 4.92 by that to the minus 2 divided by 1.09 basically. And we end up with an S of, we'll call it 4.5 times 10 to the minus 2 in terms of our solubility in this compound. That is the solubility of really our silver chloride as well, because when we look at it, it is what S is equal to. It's a 1-to-1 relationship back this way, which means our molar solubility of the silver chloride would also be this as well. So kind of like what we talked about when we were talking about KSP, that basically when you do solve for that, excuse me, when you do solve for that S, it is basically the solubility of the whole compound there, and you can equal that. Now, just for reference point, if you remember when we did something like just silver chloride in water, when we were talking about our KSP, that basically will get you S squared equals a KSP, which gives you something like S is equal to, I think it's 1.3 to the minus 5. So what I just did here would be the solubility of silver chloride in water. And you could see that the solubility of it in ammonia is much, much higher. So just for reference point there, in water, you could dissolve 0.00001 moles per liter. In ammonia, you could dissolve 0.04, almost 0.05 moles per liter, way more soluble in the ammonia than in water in that particular case. And that is why when you do that part in group number 1, you use ammonia basically to rip out the silver from the solid, because once that ammonia is present, it is very much wanting to form that complex ion because of that KF value. So the formation of a complex ion wants to happen. And if you remember, what you do at the end is you add some nitric acid, right? That nitric acid is going to change the pH and kind of free up the ammonia, right? It's going to get rid of the ammonia at that group 1. And what that's going to do is then liberate your silver ions again, right? And if you remember in group 1, what you look for is you add ammonia, solid goes away for silver. You add nitric acid, the solid reappears. And it's able to reappear because if you look at this overall reaction right here, once that silver is liberated from the ammonia, by dropping that pH a lot by adding the nitric acid, there is still chloride ions floating around. And that allows the silver and the chloride to come back together to form that white solid that you see in group 1 of qualitative analysis, where white solid, add ammonia, disappears, add nitric acid, white solid comes back again by adding nitric acid. Obviously, nitric acid and ammonia, weak base, sort of liberates the silver ions from it and allows it to find the chloride now, which is its next best option because the amount of ammonia now has dropped significantly in that solution when you add the nitric acid. And that's going to allow the silver then to go, okay, I'll just go back with my chloride there and make this solid and reform. Any questions on that? All right, so that is the end of chapter 16, I guess. So we are down to one more chapter to go, which is chapter 12 in kinetics. Obviously, we will tackle that next week. And then we have one more week. We are down to, what do they say, 8 days. Yes, on 2 hands, almost 1 hand at this point. So down to 8 days to go. A lot going on in the 8 days, another exam and a final, you know, some general unknown next week and all that good stuff. So we have lab today, which is about, so it should be pretty good little review lab and all that good stuff, complex ions, coordination, compounds, all that kind of stuff. It's an activity. There's a video. I'm not sure yet how much of that we're going to watch or not, because she kind of does something a little bit different that's on the, than that, what's in the activity, but we'll talk about it when we get there. Any questions on anything here going on? Okay, so we went a little bit long. So why don't we start at about 3:10, stretch your legs and all that good stuff, and we'll see everybody in lab. Hopefully the lab connection there will work. I apologize again for that. So if you didn't type here, make sure you do type here, and then I'll see everybody about 3:10, about 3:10.